Okay, hello. This is our third video, our third lecture in the series Transient Signals on Transmission Lines. In this lecture, we'll be building up the details of how voltages and currents go from one end of a transmission line to the other. And in particular, we'll be discussing transmission lines that end with resistors or resistive loads on the other end. So we talked about this in the last couple lectures, but this is a picture of what looks like a simple circuit where you have a battery, a switch, and a light bulb, and we can typically represent a light bulb as a resistor. And if we close the switch, then it should immediately establish a current that flows, in this case, clockwise. The current will flow through the battery. And if you know the resistance of this battery, then the current would just be I equals V over R would be that current. And so that's a pretty simple and easy relationship. But as we discussed, this kind of conflicts with Einstein's special theory of relativity, which essentially says, amongst other things, that information cannot travel faster than the speed of light, which is about 3 times 10 to the 8th meters per second. So if the battery and the light bulb are separated by any physical distance, then we can't have instantaneous transmission of information. So the moment you close that switch, the thought exercise is, how does the battery know that the light bulb is there? And how does it know the amount of current that it needs to provide? There has to be some process of that occurring. And that's primarily why we have to consider this not as a single circuit that's instantaneously small, but as a transmission line. There will be a back and forth process of the battery sort of finding out what is at the load and establishing that proper current that we know will be the case from basic circuit theory. So maybe you've seen this before if you've turned on an oscilloscope and plugged it into some sort of a digital circuit. And maybe your digital circuit has some sort of a square wave or clock or some rapid up and down square wave pulses that you're putting in there. And you expect it to remain clean, but maybe at some point you touch your oscilloscope to a different place in a circuit, and you see this weird thing, what you see on the right, where instead of having a nice, perfect brick wall, you have the signal kind of overshoot and oscillate back and forth until it settles out. And then when the signal rises again, you see the exact opposite, where you see this overshooting and gradually approaching where it is that it needs to go. Maybe you looked at it and said, whatever, I have a bad scope, or it's a bad measurement, or who cares, it looks like a pretty good square wave. And maybe your instructor called this ringing or put some term for it. But what we're going to find out today and in the future is that this is actually a real phenomenon, a real transmission line effect. And this is basically evidence of the fact that there's a physical separation between the source and between the receiver, in this case, between the oscilloscope and whatever it is in your circuit that's powering the voltage. And so you can actually measure the finite back and forth delays. If you take that velocity and divide it by the distances, that's going to correspond roughly to the time scale of these oscillations, and that's not going to be a coincidence. So let's dive into how exactly this happens throughout this lecture and try to build up the physics and the understanding of that. So I've divided this lecture up into 3 videos. The first, we're going to talk about the initial stage when a circuit is connected or when a switch is closed that first establishes a voltage on a circuit. Then we're going to talk about the reflections, this ping pong game that's going to go back and forth between a source side and a load side. And then we're going to introduce a technique called bounce diagrams, which is a nice way to visually keep track of everything. I'll go from there. So we'll start out with part 1 in this video, which is on the initial wave propagation. All right, so I'm going to draw a transmission line in what will hopefully soon be a familiar way. I'm going to start out with a battery here. It's going to be connected to a resistance. This battery will have a voltage value of V sub G, G for generator, and it will have an internal resistance associated with it that is R sub G, right? This is what we're going to call the generator voltage. It represents the fact that no battery, no voltage source is perfect. There will be some resistance associated with all of that. All right, now we're going to have a switch that is going to connect this battery resistor combination to a transmission line. And the transmission line I'm going to represent with these 2 tubes. look like this. Do my best to draw on this little tablet I've got. Not bad. All right, I'll connect that right there. Again, this tube represents a transmission line, which is just a fancy way of saying that we have a finite delay from one end to the other. All right, the most important property of a transmission line, really, there's two. There's a propagation velocity, and then there's the intrinsic impedance. The intrinsic impedance often is called Z0, and that defines the ratio of voltage to current for any wave that is traveling along this transmission line. And on the other end of the transmission line, we call that the load. And we're going to assume for today that that load is a resistor and it has value of R sub L. All right, so this is a circuit we're going to consider. And what we're going to say is that at t equals 0, this switch is going to close. All right, and we're going to ask the question of what happens. All right, and again, we're starting out before t equals 0. We have no voltage, no current, everything is dead. There's that battery ready to connect, but none of that voltage or current is on the transmission line. All right, so beforehand, we're basically going to have a situation where the source sees this, right? We've got the source, we've got the connector connected to the generator voltage, and here's a switch, and that's the end, right? This is what we would see at t equals, I'm going to write 0 minus, since it's right before that switch closes. All right, so first question, what happens right after the switch closes, right? That's going to be the critical first question. All right, so let's write down this RG. And now all of a sudden, we have connected this to the transmission line. Now we know, you and I, looking at this diagram, that on the other side of this transmission line is RL, this load resistor. But the battery doesn't know that yet. It has absolutely no idea what's on the other end of this transmission line. All it knows is that it's connected to a transmission line. Now, what is the impedance of this transmission line? That's Z0, that's the ratio of voltage to current. So effectively, this battery right here and its resistor RG will almost think that it is connected to a little resistor that has value Z sub 0, just like that. All right, this is what the circuit looks like at t equals, I'm going to write down 0 positive since it's right after the switch closes. All right, now what we've got right here looks like a resistor divider, right? And that we've got VG, which is going to create a current across a combination of RG and Z0. Remember, Z0 has units of ohms, so it looks like it's a resistance, even though it's not really a resistance. So the first question you want to ask is, what voltage is going to appear across Z0, across the transmission line? Well, we know how to figure that out. That's going to be, I'm going to draw this out right here. We're going to call this V sub S for the voltage on the source side of the transmission line, right? Vs is voltage on the source side of the transmission line. And we can figure out what Vs is, right? Vs will be Vg times, and we're going to apply simple resistor divider rules, times Z0 divided by Z0 plus Rg. All right, so that will be the initial voltage that is placed across this resistor, right? It's going to, across the impedance of the transmission line. So as far as the source is concerned, it's as if the transmission line were a resistor of value Z0 in terms of what voltage appears across it. At the same time, there is not only going to be voltage, there is also going to be a current that will be established that will run through that Z0, and that will have a current of IS, right? I that's established on the source side of the transmission line. And what's that value going to be? So for that, we got to go back. Remember our definition of Z0, or the intrinsic impedance of the transmission line, is going to be the ratio of the voltage to current for any propagating wave that is through this transmission line. Remember, Z0, by the way, is known if you have the inductance per unit length and the capacitance per unit length of the transmission line. So figuring out what IS is pretty simple. It's just going to be the source side voltage divided by Z0. All right, so if we have the voltage, we have the current. So even though we're drawing this as a resistor and saying that this VG generator is placing a voltage Vs on this impedance Z0, it's not really a resistance in the traditional sense, right? This C0 is not burning power. What it is doing is it's transmitting that power, or it's conducting that power as a wave. And so at that very moment, we're going to kick off a wave that has voltage value Vs. And that wave is going to start moving along the transmission line toward the value R, toward the load RL. And so at the very first moment, if I plot here on this axis the voltage as a function of location Z, at the very beginning, right after the switch closes, I'm going to get a little pulse right here, and then the value is going to be 0 everywhere else across the transmission line. This basically is T equals 0 positive, right? We've just created a little pulse that just fills the very first segment of this transmission line. If we wait a little bit longer, so I'm going to write this in red and make it T equals 0 plus plus, it just means wait a little bit longer. Now this wave is going to propagate a little bit further, and now it's going to go to 0, like that. Right, you wait a little longer, and T equals 0 plus plus plus, right? Even wait longer than that, and this wave goes further. So you can see that this wave is working its way toward the load, and the intensity of that voltage is just set using resistor divider rules on the front end, and the current that rides with that wave is just going to be the voltage of that initial wave divided by Z0. So that's a simple way to establish the initial wave, where the battery has no idea what's at the load. All it sees is a transmission line, and it treats a voltage and current as if the transmission line were all that there is. So that's an important way to start. The question that we're going to answer in the next module is what happens when this wave reaches the load and encounters that load resistor. And that's going to start off the very important ping-ponging process. It's going to get us to the circuit steady state that we know should exist.